Hi, I'm Alfonso Lagares, and this is my Physics 2212 Lab 5 report, where we'll be looking into Faraday's law through magnetic field. First, I'll introduce the lab, its goals, and the fundamental principles involved in it. I will then discuss the data collection and measurements taken during this lab. The result of the lab will be interpreted and presented through a closed script model. And finally, there will be a conclusion and a couple of questions. Goals are to record the behavior of a magnet falling through an aluminum tube, a phenomenon known as magnetic braking. Then the observed behavior will be related to Faraday's law, and finally a computational model of the phenomena will be created. The fundamental laws used in this lab are Faraday's law and Viau-Savant's law. It was found that the magnet took 1.244 seconds to fall through a tube, while the model predicted that it would only take 0.299 seconds. First, experimental measurements of a bar magnet falling through an aluminum tube were taken. The bar magnet used was the same one as it was used during Lab 3, so its magnetic dipole value was known to be 1.96. The mass and radius of the magnet, as well as the length and width of the tube, were also recorded. 5 trials were conducted, and the time that took the magnet to drop through the tube was recorded. The average fall time came out to be 1.24362 seconds. This phenomenon observed was then built using closed script. The aluminum tube was simulated as a series of infinitesimally small loops, and the effect of the induced magnetic field on the aluminum tube by the bar magnet was calculated. The magnetic force on the magnet caused by these induced fields was calculated, and its effect on the fall velocity of the bar magnet was computed. The simulation outputs a velocity graph and time estimate for the magnet's fall duration as a function of its mass, length, and diameter of the tube and magnetic moment. It is interesting to note that given the magnetic moment measured for the bar magnet during Lab 3, the bar magnet should have only taken 0.299 seconds to fall through the aluminum tube. In order to achieve the magnetic braking effects measured, the magnetic dipole in the simulation had to be increased to 5.165. This means there was a significant source of error present during the Lab 3 measurements of the bar magnet magnetic dipole. If the resistivity of the conductor was reduced to 0, the current induced in every infinitesimal loop would race towards infinity, meaning that the magnet would experience stronger magnetic braking and would thus take longer to fall through the tube. If holes or slots were cut in the tube, the current in each ring would decrease, resulting in a quicker fall through the magnet.